So sorry, guys. I needed to run over a little bit into the another presentation here, but we left off talking about some of the really unique properties of water and the fact that they're all caused by hydrogen bonding. And the very last one we were talking about is that water makes a really good solvent, which means that it's good at dissolving other materials, which we would call solutes. And that's good because lots of chemical processes that make life possible occur in water. So water has to be really good at taking lots of different types of solutes and being able to dissolve them for the chemical reactions to occur. We're going to move into kind of the final property of water that makes it unique and makes it relevant to life. And it's kind of a little mini lesson all in itself, so it works out that we have another little video here. So a final property of water is that naturally, and you might not think of it, but it's kind of interesting. Naturally, water we think of as H2O, kind of this nice Mickey Mouse looking molecule here, right? Here's our big oxygen molecule, and here's our two smaller covalently bonded hydrogen molecules. Okay, but water naturally actually does something called dissociates, or we call it the dissociation of water. And when water dissociates, that simply means that its hydrogens and its oxygens break apart from each other. So dissociation just means to break apart. And like I said, this is happening all the time in water. We just aren't necessarily always aware of it. Okay? So when water dissociates, it forms two separate, what are called ions, positively and negatively charged molecules. Okay. And the negatively charged ion that it forms is called the hydroxide ion. So the oxygen and the hydrogen, at least one of the hydrogens, stay together to make a negatively charged ion called hydroxide. And then we call the one thing that's left, which is just a single hydrogen, all by itself, we call that a hydrogen ion, and it's positively charged. So we have a hydroxide ion that's negative, right? Here's the negative charge, and a hydrogen ion that is positive. Okay, so this dissociation of water makes something possible, or gives us the phenomenon of what we call pH. And the pH scale undoubtedly is something that you have worked with before in school, in middle school, or in ninth grade, possibly in physical science. But the pH scale is a scale based really from 0, even though we don't see 0 here, so kind of from 0 all the way up to, that nice straight arrow, 14, or from 14 all the way down to 0, however you choose to look at it. So it's a scale from 0 to 14, and basically what it's used to do is to measure the amounts of, sorry, just to backtrack here for a second, measure the amounts of hydroxide ions or the amounts of hydrogen ions that are present when some substance gets mixed with water. So when we go back to this pH scale, again, from 0 to 14, it's helping us determine how much negatively charged hydroxide ions or positively charged hydrogen ions exist when water naturally dissociates. And there's really 3 categories of materials that we talk about when we're looking at the pH scale. We're looking at things that are called acids, so materials or substances that are acidic. We're looking at things called bases. Here it says alkali, but that's just a fancy word for base. So we're looking at things that are bases or alkalines. And then there's also a possibility of something that we call a neutral substance. Okay, so here's kind of the difference here. These acidic substances have a greater concentration of your hydrogen ions, or your H pluses. Okay, so whether it's a strong acid, whether it's a weak acid, we'll talk about how to determine that in a second, but more importantly is that these things have a high concentration of your H plus ions. Okay, so acids are things that have lots of these positively charged hydrogen ions. On the other hand, bases, or these alkalines, as they say here, but again, it's just a fancy term for base, bases have a much higher concentration of the OH, or the hydroxide negative ions. Okay, so when water splits up, if you're getting lots and lots and lots of H pluses, lots and lots of positive hydrogen ions, you're dealing with a substance that's an acid. And when water splits up, if you're getting lots and lots of OH minuses or negatively charged hydroxide ions, you're dealing with something that's an alkali or a base. Okay. It's no coincidence that we consider pure water a neutral substance. So again, pure water, which is what a lot of life is based on, and this whole lesson is about water, is considered to be neutral. But that should make sense, because look what happens when you stick these two things together. You're back with good old HOH, or in other words, H2O. Okay, so if we take the H plus ions that makes substances very acidic, and we take the OH minus ions that make things very basic, and we stick them together, we no longer have an acid, we no longer have a base, we have HOH or H2O, and we have water, and water is considered to be perfectly neutral. Now, in terms of the scale, you can just see by looking at this that things that are acids, and again, we'll talk about strong and weak acids in a second, but if it's an acid, it's really kind of in this 0 to 6 range, more or less. Okay? If it's a base, it's in the kind of 8 to 14 range. So from 8 to 14 are your bases, and then right here in the middle, that 7 pH is considered to be neutral. So the low numbers, 0 to 6, are your acids. The high numbers, 8 to 14, are your bases. And then right smack in the middle, 7 is considered neutral. And that's where, again, we say pure water is. Okay? Now, in terms of how we determine how strong or how weak these substances are, a good general rule of thumb is the further away you get from neutral, the further you get from 7, the stronger of a substance, the stronger material you are. Okay? So substances that are way down here in that 0 to 3 range, a long ways away from 7, they're your strong acids. Okay, they're acids because they're less than 7 on the pH scale, and they're strong because they're pretty far away from 7. As you start to get closer to 7, the 4, 5s, and 6s, they're still acids, but they're considered a little bit more weak. Okay? And on the flip side, a really long ways away from 7, the 12s, 13s, and 14s, those are bases because they're greater than 7, and they're strong bases because they're a long ways away from 7. Then when you get to like the 8s, 9s, and 10s, you're closer to 7. You're still greater than 7, so you're dealing with a base still, but because you're closer, you are looking at a weak base. Okay? So just in general, familiarize yourself with the pH scale. If you don't know it already, understand what the different numbers mean, and that 7 is perfect neutral, less than 7 are acids, greater than 7 are bases, and then if you're close, tucked in here close to 7, you're fairly weak, and the farther you get from 7, either less than or greater than, you become a much stronger substance. Okay, and then also please remember that what determines acids is these high amounts of H plus ions, and what determines bases are these high amounts of OH minus ions, which makes water, a combination of the two, that perfectly neutral substance right in the middle. And then the final concept we need to talk about as we discuss the pH scale heading into the rest of the week is the concept of a buffer. So a buffer is critical. Buffers in general are critical to biological systems, to keeping life around on our planet. The reason is because we're constantly exposed to really acidic and really basic environments. We're exposed to environments that are these wide ranges of pHs, but our bodies, if I can go back for a second, like to be right in this neutral range. So even though we get exposed to acids, and even though we get exposed to bases, our bodies don't work unless they stay right in this kind of 7 range right here. This is where our bodies like to live. Okay? So if I go back to this picture for a second, it's not very scientific, but it does represent the role of a buffer. Okay? When things start to pile up, right? When things are getting a little bit crazy, when the environment is getting a little too acidic or a little bit too basic, and it seems like the scale is tipping, the role of a buffer, which is represented by this larger ball here, is to kind of reestablish that balance. So let's say, for example, and again, this isn't a very scientific drawing, but let's say this is all representing, this is becoming acidic, okay? So let's just say over here, we're dealing with an environment that is very acidic. Okay, so it's obviously tipping the scales kind of in this direction. Okay, if that goes unchecked, the scale is going to completely tip. Our environment is going to be so acidic that life is not going to be able to exist within it. Okay, but the role of a buffer, sorry, it takes me a second to jot down the words here. The role of a buffer is to reestablish balance to that scale. Okay, so buffers are kind of weaker acids and weaker bases that counteract the effects of stronger acids and stronger bases. Okay, so if things were becoming very, very, very acidic, this buffer here might be a weak base. And when you combine things that are getting very acidic with a weak base, you work them back toward that neutral 7 or that balanced, straight across scale. Okay, so if here we have things that are getting down into the 4, 3, 2 range on the pH scale, and we add a buffer that's a weak base, maybe something that's like an 8, 9, maybe a 10, we start to reestablish that balance. We start to get closer to our pH of 7, and therefore life can continue to live within that nice neutral range. So the role of a buffer, which is usually just a weak acid or a weak base, is to counteract the effects of strong acids and strong bases to make sure that life can exist at this balanced state, that neutral state, right around a pH of 7.